Hi there, my name is Angela Oldham. I'm an engineering student at RMIT in my semi-final year, and during this crazy pandemic year, I've worked with Bosch to create something I think would interest you, something called a compact battery supply. Let's go for a walk. Have you ever wondered how those devices that seem so far away, like the sensors in farms and GPS trackers, how they always seem to have consistent power? You need to find a way to still be able to collect data. You want it to be small, compact, but still be able to power this device that's tracking how the soil's going or where your shipment is. So in order to be able to limit how much exposure your sensor or your device is getting, you need a battery that is able to last a long time and power your device, your sensor. This is what I've done. The Bosch team and I have come together to create such a device. It's a compact battery supply where store-bought batteries are powering said device to be able to output 3.3 volts with 1 amps for 7 seconds. This can be challenging because a lot of these devices that are already out there require you to purchase powerful lithium-ion batteries, and sometimes rechargeable, which can cost you. Alright, so this is the behavior of like any battery. It'll start at 1.5 volts or whatever the nominal voltage of that battery is, and then as time increases, it'll lose its power. This is why we have to be able to store the battery in something so that it's able to last a lot longer. But for us to get a longer duration, we need to find a battery with the highest capacity. You can easily find this in data sheets. I'm sure you've heard of all the different sizes and types of batteries in stores. There's AAA, AA, C, D, and other various types, but we'll focus on these for now. We wanted batteries that were easily accessible, so I based my comparisons and research on what I found in store. We can see here that alkaline D batteries are the highest capacity rating, because even though the AA lithium-ion batteries are very high for their size, there isn't anything larger than AA. Plus, if there was, it would be super expensive. The price points drive an important comparison. The alkaline D batteries are a lot cheaper per battery than lithium-ion, so this ended up being the chosen battery to work our circuit around. Now, since this is an alkaline battery, we want to make sure that it lasts as long as possible. Alkaline is best used for low drainage conditions, such as TV remotes, since they're not used as often as cameras, which prefer lithium-ion. Our circuit only needs to output a hefty 3.3 volts with 1 amp for 7 seconds. And that's only every 15 minutes, so we need to figure out how we can drain as much of that capacity within the battery efficiently. This brings in trickle charging, which feeds from the battery at a super low voltage that slowly builds and builds into the storage within the 14 minutes and 53 seconds that we have before we need to burst that high power output. So where does that leave us with storing our energy? We can't use batteries because they deplete with value over time. We have to look into capacitors. They're really great for storing high energy and it's able to continuously burst repetitively over time. Now for capacitors, they have the same behavior as that of a battery, where it'll have the highest capacitance, and then as time decreases, they'll get down to, let's say, 0.8 farads. Just an approximation. So the benefit of using a capacitor is that they'll continuously store 2 farads. You can keep recharging them for them to repeat the same behavior. Our challenge was that we needed a capacitor that sat above 1 amp as it's discharging for the 7-second duration. So this needed to be 7 seconds. Now, there was a lot of talk on whether or not we use a high capacitor with low voltage or a low capacitor with high voltage. Based on this relationship, where current is equal to capacitor times rated voltage, the rated voltage and capacitor is able to mix between different values in order to obtain the same current value. Let's go to the simulations. Both graphs represent the behavior of a small capacitor with large voltage. Even with various loads, the capacitance doesn't want to last long and will always have a fast drop rating due to the lack of storage within the capacitor. These graphs represent the behavior of a large capacitor with small voltage. We can see that the duration of the capacitor will last for as long as we need, being the 7 seconds. Now that the rated capacitor needed to sit at least 25 farads, we look at choices available for purchasing. I brought up different variations that allows a constant voltage at 1.5 amps and 2 amps, meaning they were large enough to not overuse or overheat and deplete during time. Due to the minimum value of 25 farad, the Bosch team and I wanted to make sure the capacitor was able to hold out for as long as needed, so the 30 farad and 40 farad choices were decided. Initially, both capacitors were chosen to be tested side by side, but due to COVID, it limited our research since we weren't able to order them in time to test. This meant our whole design needed to be simulated in order to prove that this works. This brings us to converters. Now, our layout so far needed input of 2 to 4 volts and an output of 3.3 volts at 1 amp. So we've got 2 batteries in series that'll be around 3.1 volts to 3.0 volts going into the circuit. Because the circuit is trickle charging, we need a buck boost in between the battery and the capacitor where energy is being stored. Now the capacitor has a rated voltage between 2.3 volts and 2.7 volts, meaning that's when it's active and storing. So we need a buck boost in between that is able to collect the 2 to 4 volts and output between 2.3 to 2.7 volts. So once the circuit needs to burst out those 3.3 volts at 1 amps, because the behavior of the capacitor is decreasing through time, we need a buck boost in between the capacitor and the output to be able to sit at a constant rate of 3.3 volts at 1 amp. Oh, here we are. Now we choose buck boost converters because the control it provides is a lot more comforting than that of just a boost converter. A buck wasn't necessary since we wanted to go from a lower voltage to a high voltage or just a constant higher voltage. We needed to increase, which is boost, and boost is generally used for high voltage situations since it just keeps on building and building and building. And so we discussed that having a buck boost has a lot more control in its ability to make sure that the supercapacitor isn't overly charged or undercharged, as well as that the output is able to sit at the constant rating that we want it to. Okay, now we've got all of our components that fit nicely. We need to control this somehow. Microcontrollers. But let's go outside. My legs need a stretch. Initially, our plan was to use the current Bosch microcontroller they already had. We used it as a temporary microcontroller and not as the finalized microcontroller due to its size. We wanted this design to be as compact and small as possible so that it's attractive for other customers to use on their designs. Alright, let's get to the final simulations. Okay, so on the left corner we see the batteries feeding into the protection circuit, then into the input of the buck boost converter. We see here in this graph that it will input 3 volts into the first buck boost. We're checking the output of the buck boost and we're getting 2.45 volts. This can be changed based on the voltage divider. But since the capacitor needs an input voltage of 2.3 volts to 2.7 volts, we want to sit in the middle. So this feeds into the capacitor. For the sake of the simulation consistencies, I want to use 30 farads. But due to its large storage size, it took a toll on my computer process and would either crash or just take too long to simulate. I used 30 microfarads for the sake of the computer processing power, and at the time I could use effectively. We can see that the capacitor reaches 3.3 volts and the 1.1 amps that was necessary. However, due to the size of the simulated capacitor, it wasn't able to hold out as long. Regardless, this proves that our capacitor would be able to reach the desired output and would be able to last during the 7 seconds. And in order to simulate it realistically, we used an inverse and pulse modulation to act as when the circuit flips from one buck boost to the other. Thank you for listening to me talk about my final year project. It's been such a wonderful learning experience for me to work with Bosch on a device such as this. Feel free to send me feedback. Thank you.